The next speaker is remotely connected. Can we check if the connection is up?
Can you hear me?
Yes, we can. So yeah, the next speaker is Spencer Biale, and he's from the University of Victoria, and I think he will show us a little bit more on this machine learning approach. Please, Spencer, go ahead.
Sure. Hopefully that is sharing. Yeah, thank you for the introduction. Good morning and good afternoon to everyone. I'm really happy to be here to talk about this really fun project that I got to work on recently. With the help of Sarah Lucatello, who I believe is in attendance. Hello, Sarah. And my supervisors, Kim Van and Sebastian Fabro. I looked into addressing a more downstream problem. If and when a stellar spectrum is contaminated by light from a satellite, can we still do anything useful with that spectrum? And more specifically, can we use machine learning to help us? The project is very cleverly called Star Unlink, and I'm allowed to say it's clever because I did not come up with the name. My supervisor, Kim, did. So we're all aware that satellite megaconstellations pose a problem for astronomy, but maybe we're not all familiar with the full extent. And it's clear from some of the talks at the symposium that we're still trying to figure out all the details. But there have been studies that tried to quantify how bad it will be for spectroscopic surveys. In a 2020 paper, and as Olivier detailed in his talk that happened right after lunch, it was found that up to several percent of spectra in a survey like WEAVE could be contaminated. Several percent is a massive number, so that's definitely going to be problematic. Another study looked at the projected distribution of satellites in the sky at a given time of night and produced a very useful online tool that shows the distribution on the sky, the satellites along with their brightness. So it shows satellites from these different companies. And basically it's a lot of satellites and they're very bright. But you have to remember that they only cross a star for a fraction of a second, and the integration times for WEAVE are going to be hundreds of seconds. So how bright will they be, really? This plot is from a 2022 study in which they determine the effective magnitude of satellites as a function of their altitude. And the color of the line corresponds to different integration times, where you have a 1 second integration in the middle of the plot, corresponding to a relatively bright satellite, and a 20-minute integration time at the bottom of the plot, corresponding to a relatively faint satellite. So yes, most of the satellites have an altitude between 500 to 1,000 kilometers, and most of WEAVE's integration time will be around 20 minutes. So this is our region of interest. Turns out that the limiting magnitude of the low resolution mode of WEAVE is about 21, which falls in this region. So the level of contamination in the stellar spectra could be quite significant. So we asked ourselves a few questions. Can we detect when a spectrum has been contaminated? And if a spectrum is contaminated, can we remove the contamination? And can we predict stellar parameters accurately despite there being contamination? And we came up with a solution called Star Unlink, which attempts to address these questions. And I'll very briefly go over the implementation details here. So we start with one data set of spectra. They are clean spectra without any contamination. A satellite is reflecting sunlight, so we can artificially contaminate these spectra by adding solar spectra to them. In practice, of course, as we just heard, it won't be a perfect solar spectrum. It will be modulated by the reflectance properties of the satellites themselves. But for this study, we assumed we knew the contamination perfectly to see what kind of results we would get in a best case scenario. So from there, you get a second contaminated data set with a variety of signal to noise ratios, levels of contamination, and for the stellar spectra, the radial velocities change. Because we artificially contaminated the spectra, we always know what the ground truth is and what the clean spectra are, or what they should be. So we can give various tasks to machine learning methods. For example, you can ask a UNet, which is a particular kind of neural network architecture, to take contaminated spectra as input and output the clean spectra with the contamination removed. You can also get a convolutional neural network to predict the stellar parameters corresponding to the clean spectra. And finally, you can train a convolutional neural network on both data sets and get it to predict yes or no, is the spectrum contaminated? So we can address these questions we pose directly with machine learning. Unfortunately, I don't have time to explain the implementation details of these neural networks, but you can read our paper if you want to know more. Yeah, so for all the results I'm about to show, I used thousands of Flames UVES spectra modified to look like Weave spectra for both the training and test sets. So for detection, the neural network outputs a value between 0 and 1, corresponding to approximately how confident it is that a spectrum is contaminated. So to get a definitive decision from the network, we need to set a decision threshold above which we consider the spectrum to be contaminated. This plot is showing how the precision changes and how the number of correctly identified contaminated stars changes as we change that decision boundary. If it's really high, we have excellent precision, but recover only a small number of contaminated spectra. Whereas if it's too low, we do identify all the contaminated spectra, but we get a lot of false positives. So we choose a threshold that gives us a compromise between these two values, maybe 0.6 as shown in the plot here, which identifies about 67% of the total contaminated spectra and maintains a high precision. And of course, the majority of the contaminated spectra that aren't identified just have low levels of contamination in them. This plot shows exactly that we identify contaminated spectra more readily as the contamination levels increase. Additionally, it becomes a lot easier for the network to identify contamination when the stellar spectra have large radial velocities. This makes sense because the satellite spectra are approximately in the rest frame, so there's cleaner separation between the two spectra. All right, so if we identify a contaminated spectrum, can we just remove the contamination? This is showing 4 examples of contamination being removed by a UNet. The gray line is the contaminated spectrum. The black line is the clean spectrum, and the pink dashed line, which you can't really see very well because it usually lays right over the black line. That's the output of the UNet, which removes the contamination and predicts the clean spectrum. So we have 4 examples here showing kind of what happens when you have different metallicities and different signal to noise ratios. So these 2 first rows have high metallicity, and even with the case of the low signal to noise ratio, it's able to reproduce the spectrum quite cleanly. And then these 2 bottom row examples have low metallicity, and in both cases, even with high signal to noise ratio, you can see that it does have some difficulties reproducing the spectra. So it definitely seems like low metallicity is a problem here, and it's likely just because that there aren't that many low metallicity stars in the training sample, so the neural network can't learn very easily the information. Here I'm showing the performance across the entire set of spectra, split into 5 different groups of increasing levels of contamination. The y-axis is showing the relative errors of the predicted and clean spectra. And the main takeaway here is that the UNet can reconstruct the clean spectra, even in the cases of worst contamination, to less than 1% error, with some slightly larger errors around the deeper absorption features. So we can fairly effectively remove the contamination. But what about stellar parameter estimates? So this figure is showing the prediction errors of stellar parameters as a function of contamination level for a few different cases. The solid lines are the average errors, and the dashed lines are the standard deviation of the errors. So the purple line in all these plots for temperature, surface gravity, metallicity, etc., is showing what happens for a convolutional neural network of CNN trained on only clean spectra, so it doesn't understand what contamination is, its prediction errors get worse with increasing levels of contamination, as you would expect. The orange line is showing what happens if we instead include contaminated spectra in the training set. So it actually learns what contamination is and can sort of see through it. Across all levels of contamination, its performance is consistently quite excellent. And the green line is showing what happens when, again, we have a CNN only trained on clean spectra, so it doesn't understand what contamination is, but it's predicting on spectra that had their contamination removed by the UNet. It has a similarly consistent performance as a CNN trained on contaminated spectra. It's a little bit worse, but it's very similar. So we are seeing that machine learning methods can clearly understand the contamination that is happening and produce accurate stellar parameter predictions. The UNet can take a collection of contaminated spectra, remove the contamination, and produce a set of clean spectra for any other downstream task. So we wanted to show the versatility of this method by using a completely different stellar parameter estimation method called the canon on these spectra to show the improvements in the predictions that can happen. So I'm showing the prediction residuals on the contaminated spectra in gray versus the spectra with their contamination removed with the UNet in red. So you can see for these three stellar parameters here, you get significant improvements in prediction quality when the UNet is used to remove the contamination. One of the main problems seems to be when predicting on solar twins. Since the contamination is reflected solar light, it's difficult to disentangle that from a stellar spectrum that's almost identical to a solar spectrum. So I'm showing here the prediction residuals of a test set of solar twins in orange and versus the residuals of the rest of the test set in gray. You can see pretty clear biases in the temperature predictions, calcium predictions, and magnesium predictions, and maybe some of the other parameters. But I also want to note that the solar twins test set was quite small. So we are affected by small number of statistics here, but it does seem fairly clear that there are issues with solar twins.
Around 3 minutes.
Thank you. Yeah, this is my last slide. Yeah, so with Star Unlink, we can do a few things. We can detect contaminated spectra with fairly high precision, but we, of course, miss some of those spectra with low levels of contamination. We can remove the contamination with a UNet with a less than 1% reconstruction error. And the problem there is low metallicity and low signal-to-noise ratios. And also we can predict stellar parameters of contaminated spectra accurately. The problem here is solar twins. I also wanted to mention that even in the cases of like very low levels of contamination, like 1% or so, the CNN can still predict stellar parameters of those stars very accurately. So even if we can't detect them, we can still use a CNN to predict stellar parameters of all the spectra in a survey that has been trained with contamination in the training set. I do want to reemphasize that the results I showed here are for the best case scenario when we understand the contamination perfectly. The various satellites will impart their own signatures to the reflected solar light, so it would benefit our method a lot to use the reflectance properties of the satellites in our training sets. This information can come from the companies themselves, or we could intentionally observe stars that we know will have a satellite cross their path to collect that information ourselves, or use a method described in the previous talk. But yeah, that's it for me. So if you want to know more, you can just see our paper in the monthly notices. So thank you.
Thanks a lot. We have time for a question. Yes?
I have a question online.
Oh.
Please.
Okay, please go ahead, yeah.
Let's do your live first, maybe. Go ahead online.
Hi, Spencer. Very nice talk. I think that the result is for absorption lines in the spectra. Can the method be used for galaxy spectra with contaminant emission lines?
Yeah, I don't see why not. It would just it just matters how you create the training data set. As long as you know how the contamination would affect your galaxy spectrum, then yeah, you just add on the contamination and train a neural network.
I think so. We will need environmental parameters as well, because the emission lines can be created based on the mostly environmental parameters.
Right. Yeah, galaxy, that's not my field, but as long as you understand how the spectrum would be affected, then I think, yeah, this method can be adapted pretty easily.
Thank you so much.
Thanks, Spencer, for the excellent talk. Just one quick question. So one comment before that, maybe you're pointing out that this is the best case scenario, and I would really, I can't stress this enough, because real spectra of stars, sometimes don't quite look like the training spectra, and I would be extremely interested in, have you tried this on a real, actually, stellar spectra with the stellar parameter recovery?
Sorry, if I have used this on real spectra?
Yes, I mean real spectra from, some survey.
Yeah, well, I guess the training set and my test sets were real spectra, but I didn't get to, I don't have a test set of known contaminated spectra with real satellite contamination. I only used my own artificially contaminated spectra, so I haven't gotten a chance to actually test this on real spectra yet.
Yeah, so that's exactly my point, and it would be really cool to follow up on that and then see the numbers, what they look like. Thanks.
Definitely. Thank you.